And last week we checked that sharing screen works fine, including videos. So
We hope so.
Stop transcription. Yeah, because we do not need transcription. Yes. Yes, 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 yes. And before we start our seminar, just a moment. Okay, I believe people are still coming, but congratulations to Mark Bly with professor position. So that is very good news, and just before Christmas, so that is the kind of encouraging, really good news. So congratulations, Mark. And yeah, and our seminar today is by Matt Turner. Matt is a good friend of our school for many years, and it's a pleasure to introduce him and introduce his talk today. Moreover, the Matt was in I don't know, did you cooperate, did you publish paper with Mark Cooker? I'm not sure.
No, I haven't. No, I'll say a bit about that in a minute.
Yeah. Yes, yeah. So the now it's yours. So I mean the floor is yours. So then please switch off. I mean all of us except of the Matt to switch off your cameras and microphone. So Paul, please do this, and if not, then I'll switch on your behalf. Then I'll switch off my camera and microphone as well. But I will be here, Matt. So if something happen, you can call me, and I will be here. But without the microphone from others, the quality is really better. So Matt, please start your presentation, and you wanted to say something about something. Okay, yours.
Yep. Thank you very much. Yeah, and do pipe up if you can't hear me or something doesn't look particularly right. Otherwise, I'm just talking at a screen for an hour. Okay, well, thank you very much. Thank you for inviting me to give a virtual seminar. Unfortunately, it's not face-to-face, but you know, maybe next year or the year after, we'll be able to have a few more face-to-face events. So I'm going to talk today about some work I did during lockdown, in fact, when I was first shut away on vortex leapfrogging external to a circular cylinder. But before I start that, I'm just going to give a little, as this is to commemorate Mark's retirement, I'm just going to give a few Mark Cooker highlights before getting into the actual part of the talk. So I first met Mark back in 1998 as a very eager undergraduate student. I remember Mark was my tutor for calculus, and I remember it very vividly because on that first Monday at 5 o'clock when we were supposed to have this seminar, all of the electricity went out in the arts block, and so we ended up having this seminar in his office, a very dark and dingy office, but because it was a very grey day that day. But I just remember thinking, this guy's interesting. He's definitely a good mathematician, and my instincts turned out to be correct. So Mark's taught me many courses. I thought I'd just list them for novelty's sake. You know, advanced calculus, mathematics of diffusion, fluid dynamics, and you know, every lecture course I've ever had with Mark, it's always been so immaculately prepared, so much so in fact that I would be a bit embarrassed to show him my third year fluid dynamics notes because they're quite similar to what I was taught when I was an undergraduate, because they were that good. I thought I would use them. Mark went on to be my internal PhD examiner in about 2002, and absolutely no spelling errors got through as far as I can tell. A few other typos that I found a bit later, but no spelling errors. Mark was completely on the ball as my internal. But what I can say about Mark is he's always supportive, very willing to talk and have a look at material you've got. think Mark is a really calm influence. And I've, when I've been a bit upset, it's always been really nice to talk to Mark because he's very calming in that way. And I've put here central admin in brackets because this sort of just reminds me that I very rarely ever saw Mark upset or angry, but whenever I did, it always seemed to have something to do with some sort of central admin team or something. I don't know whether that's always the case now, but yeah, he was always very calm, apart from, I say, on a few occasions where I've caught him a little bit upset about something that the central team has inflicted on him. And he's hugely knowledgeable on many topics, some that I was surprised he knew so much about. And this is what I like about talking to Mark. He knows so much about so many different things. He's also obviously a great beer drinking and curry eating companion, and I hope he'll still come and visit Surrey in the future. But as Sasha said, did I write a paper with Mark? Well, no, that's my biggest regret, that we never wrote a paper together. But I just note that there is still time, Mark, if we can find something to write something about. Okay, so on to my talk for today. So these vortex leapfrogging external to a circular cylinder. So what are we interested in? Well, we're interested in what different types of coupled vortex motion can be achieved by, say, two line vortices outside a circular cylinder. And in particular, we are looking to identify when something called leapfrogging occurs, and I'll say a bit more about what leapfrogging is in a moment if you don't know what that is. We hope to see whether the process we use to identify when leapfrogging occurs, hopefully we can extend any analytical approach to other geometries. And why do we want to do this? Well, say computing the motion of line vortices in the plane can be a really good model for approximating 2D vortices in things like the atmosphere and oceans. So understanding their motion is important and has interest in other areas. Okay, so a little bit about the background before I talk about the circular cylinder. I just want to talk about the planar case and a little bit of background. I know that fluid dynamics is a massive subject at UEA, so I'm sure you all know most of this, but it's worthwhile just having a little background. Okay, so for a single line vortex in the plane, in an inviscid incompressible fluid, a line vortex has a flow field that's described by one of these two quantities, so either the velocity potential, phi, being gamma over 2 pi times theta, or the stream function psi, which is minus gamma over 2 pi log r, where here r and theta are the plane polar coordinates, and gamma is the vortex strength and is in fact given by the vortex circulation. But you can just think of it as being a constant quantity that sort of says how fast these little vortices are spinning. So what does the fluid velocity look like? Well, I just alluded to it by saying this this is a sort of spinning fluid. So the velocity field u is given by the gradient of phi in an incompressible irrotational fluid, and that just has this quantity here. So this is a constant gamma over 2 pi times 1 over r in the theta hat direction. So this would be lines of constant r circular motion, and it becomes weaker as you go further out. So these are sort of faster flows in the middle, weaker as you go further out. We can also write this flow field in terms of something called a complex potential, which we denote by W, and that's the velocity potential phi plus I times the stream function psi. And in this case, for a single vortex, it's just, again, this quantity gamma over 2 pi, where gamma is the circulation log of z minus z0. And z0 is the complex position of the center of the vortex. So in this case, this z0 would be the origin, and z is the usual polar representation of a complex number, r e to the I theta. Okay, so what happens as you increase the number of vortices. So we want to look at two vortices outside a plane, so outside a cylinder. So what happens for two vortices? Well, as both these quantities phi and psi to satisfy Laplace's equation, a linear PDE, then we can just add these solutions together, and the same is true in the complex potential, to generate a new flow field. So for example, if I take one vortex, strength gamma 1 at some point Z1, and another vortex, strength gamma 2 at some point Z2, then this complex potential defines the flow field. And then in this case, what happens is, so for this particular example, if gamma 1 and gamma 2 are the same sign, then this flow field from vortex 2, if you sort of move out and look at it at the point of the center of vortex 1, is sort of pushing the fluid upwards, whereas the vortex, the flow due to vortex 1 of the center of vortex 2 is sort of pushing it downwards. So there's an instantaneous motion where this is moving upwards and this is moving downwards. And so these vortices force each other to move. And so the question is then, if we put them outside of geometries, i.e. outside of a plane wall or a cylinder, what do their respective motions look like? Okay, so when we got these two vortices next to a wall, we can, well, okay, so let's say, in fact, let's say it a different way. Let's consider a special case where this strength gamma 1 is equal and opposite of the strength of the second vortex gamma 2, and let's place them, one at position AI in the complex plane and one at minus AI. Then hopefully my video works. Then what we get in that case is just a vortex pair moving along as a pair, one vortex, the blue vortex here, one vortex, the red vortex. They move along as a pair. And this is also the model you can use when we just consider one vortex, but with a solid wall along the line y equals 0 along here. So see if I can go back. Yep. Okay. Okay, so now what happens when we have two vortices and a wall? Well, the two vortex problem and a wall is really a problem for four vortices. So what you have is you have two what are known as physical vortices, and then you have these two imaginary vortices, which give you the image vortices, sorry, which gives you the correct no normal flow condition along the solid wall. And we can write down the complex potential in the same way. We just now have four components to our complex potential. So you have this vortex, strength gamma 1 at Z1, and then you have the vortex with equal and opposite strength and the complex conjugate position, and the same for as the vortex at Z2. And so the question is, what possible motions are available in this problem? So one possible motion is vortex leapfrogging. So hopefully this video works. So this goes to YouTube. I thought I would steal. Can you see this okay? Okay, so this is...
Yeah, it's fine.
Okay, good. So this is just a simulation I took off YouTube. I didn't generate this, so I give all rights to this page. So what happens here is you have two vortex rings, and then this green ring is now speeding up and passing through the middle of the orange ring. And then as it passes through, it gets wider, the red ring contracts, and then it sort of passes through, and they repeat this motion. So you get this periodic motion, and this is what's known as vortex leapfrogging. So just come back a bit. So you have one vortex trailing another one, it passes through, and then this one now leads and the other one trails, and then the trailing one again passes through, and this process repeats. Okay, so we want to understand this. So this is vortex rings. So this is a slightly more complicated example, but if you just take a planar cut through the middle of these vortex rings, that's equivalent to having 1, 2, 3, 4 vortices in a plane. And so this 4 vortices in a plane model is a good model for this vortex rings simulation. So if we can understand what's going on in the case of these four vortices, we should hopefully understand what's going on in the vortex ring case. Okay, so there was a paper out in 2020 that I was very got the pleasure to referee, and it was by Navier-Stokes and Berkshire, who identified a mathematical criteria for when this leapfrogging occurred. So basically, they defined some. Okay, so this is our solid wall. This is the x-axis. This is the y-axis. This is the position of vortices. So it says if I put a vortex down where this square block is here, anywhere within inside this contour, my vortices will leapfrog. If I put a second vortex anywhere outside this blue contour, then there won't be any leapfrogging. Okay, and we can show that. So if I show another video. Okay, so here's a vortex. So the one vortex started at 0, 1, one started here at 0, 2. You can see this is the x and y axis, and they're basically leapfrogging along. So the blue vortex is falling behind, then moving toward the wall, speeding up, and then passing in front of the red vortex, and then the process repeats. So the red vortex is behind now, it speeds up, and it comes through. Okay, so this is obviously this is an example where they're at 0, 1 and 0, 2. So that is well inside this this region where we expect leapfrogging. But as we move towards the boundary, then this leapfrogging motion becomes much slower. So here you can see the red vortex is behind, but it's going closer to the wall. See, the axis is much more extended this time. It's a much slower process, but it moves towards the wall, eventually passes through, and now leads the blue vortex. And what will happen again, this blue vortex will slowly drift towards the wall. The red one will drift away from the wall. They'll pass over one another, and then the leapfrogging will occur. So this is right on the boundary of this leapfrogging region. Okay. And finally, if you take a spot just outside, then what happens is initially they leapfrog very quickly, do one leapfrog, but then now the red vortex just lags behind the blue vortex. It can never get close enough to influence it in order to try and leapfrog past it. And all that happens is these now just move along as a pair with no leapfrogging. Okay, let's stop there. Okay, so the question is, how did we determine such a region like this? So I'm not going to talk about the planar case. I'm going to talk about how this region is determined, but I'm going to do it for the case where instead of a planar wall, we're outside a circular cylinder. So we're going to consider some circular cylinder here, radius A. So we're going to again be think about polar coordinates. So theta is going to be the usual polar angle with the origin at the center of our cylinder. R is going to be the radial coordinates, and we've got the usual x and y coordinates. And we're going to consider two vortices outside this cylinder, one strength gamma 1 at some point z1, which you can think of as having some coordinates rho 1 and alpha 1, and these coordinates depend upon time as the vortices move, and some vortex strength gamma 2 at z2, and these will have subscripts 2, so an alpha 2 and a rho 2. Okay, so for the complex potential for this flow, to write this down, it's not quite as straightforward as the planar case, but anyone who's done some sort of elementary course on fluid mechanics, normally in viscid fluid mechanics, would have met this sort of Milne-Thomson theorem. So it says if I have a complex potential W equal to f of z, where f of z is a complex flow without the cylinder, so we just put down our two vortices, that's easy. We can do that. We saw that earlier. Then we can insert the cylinder by just modifying the complex potential to be this. So it's the same f of z, but now we add on f where we replace z by a squared over z complex conjugate. And in fact, there should be a complex conjugate over this. And then we take the complex conjugate of the whole thing. So this is a complex potential when the cylinder is present. And for our problem, we get this complex potential for W. Okay, so we can find W. So hopefully from this, we can derive our velocity equations. So that's relatively simple. The easiest way to do it is to take W here, which is phi plus I psi, and then either find the real part or the imaginary part to get phi or psi, and then from that we can get the velocity components, because we want the velocity components in terms of in the radial and theta direction, as opposed to in the x and y directions where you just differentiate this with respect to z. Okay, so if we do that and we look at the induced velocity at each of the vortices, so this would be the speed of vortex 1. This is the flow field evaluated at vortex 1, at the center of vortex 1, ignoring the term where the velocity tends to infinity. So this is the induced velocity, the induced radial velocity, d rho 1 dt, and then we have an azimuthal velocity, this rho 1 d alpha 1 dt term. And they're given, I derived in terms of the stream function, but as I say, you can do it in terms of the velocity potential if you want. So you can write down these equations, and similarly, there's a pair of equations for rho 2 and alpha 2, and it just involves a lot of swapping of rho 1s, alpha 1s and alpha 2s, and rho 1s and rho 2s, and gamma 1s and gamma 2s. So they're quite easy to write down. So you get 4 equations for these 4 unknowns, alpha 1, rho 1, alpha 2, rho 2. Okay, now this governing system, although looks a bit complicated, it is actually a Hamiltonian with respect to these conjugate variables, gamma j, rho j, and rho j alpha j. And in fact, you can write down the Hamiltonian, and it's given by this relatively complicated expression, but it's easy to go from this Hamiltonian, take the respective derivatives with respect to these conjugate variables, which I've called P and Q, but actually if you do write them down in terms of their forms in terms of rho and alpha, you get these reduces to these equations here. So you're just taking derivatives of the Hamiltonian with respect to alpha, and Hamiltonian's derivatives of the Hamiltonian with respect to rho in these combinations. And then these lead back to the 4 sets of equations we saw on the previous page. But this is really useful because obviously the Hamiltonian is a sort of measurable, it's the sum of the kinetic and potential energies of the system, and in fact then this is a conserved quantity, and so this is useful, and we'll make use of this as part of our derivation for this leapfrogging criteria. Okay, so this Hamiltonian is one conserved quantity of the system, and in fact there is a second, so it's not particularly obvious, but here's our rho 1 d rho 1 dt equation. The d rho t 2 dt equation looks very similar. These become gamma 1s. Alpha 1 and alpha 2 swap around, so these you get sign changes in here, and then these rho 1s and rho 2s swap around. But actually, if you just sort of stare at it a bit and you write it down, and then you notice if you add those 2 things together, in fact, the sum is then 0 with respect to multiplying by these gamma 1 and gamma 2. So this quantity rho 1 d rho 1 dt and gamma 2 rho 2 d rho 2 dt is 0. Thus, we integrate this and we get this conserved quantity, this rho 0. This is the absolute value of the flow momentum. And we've scaled it by this quantity gamma 1 plus gamma 2 just for convenience, but we know that that is non-zero. Why? Well, if that quantity gamma 1, gamma 2 was 0, then it produces no leapfrogging motion, because this then becomes one of our conserved quantities, rho 1 squared minus rho 2 squared. And if this is a conserved quantity, then it means that rho 1 and rho 2 can't change position. If they can't change position, then they can't leapfrog, because leapfrogging, one has to move out to a larger radius while one moves in, and they swap over. So they can't change their radial ordering, so they can't leapfrog. Okay, so we're going to just define a couple of non-dimensional quantities now. So we're going to define this capital R to be the difference of the radii squared divided by this non-dimensional, this conserved quantity, sorry, this rho 0 squared, and we'll let capital A just be the difference between these angles. So using this and the conserved quantity, it means we can write that rho 1 is this conserved quantity rho 0 multiplied by this quantity here, 1 minus g r to the half, and then rho 2 is the plus sign where this g2 becomes a g1, and these g1 and g2s are just scaled versions of these circulations with respect to gamma 1 plus gamma 2, which we know is non-zero. So G1 corresponds to the gamma 1, G2 corresponds to gamma 2. So in the non-dimensional case, we can just think of these as being constants that we can, or parameters that we can vary, and that will then we can then from those get back to what the physical circulation is. Okay, so this Hamiltonian for the system is conserved. So if we write out what that Hamiltonian is again, it's this quantity here, and I'm going to let that equal some constant. I'm going to write the constant in this form where C is some constant as well, but we're going to write it in this form. So if I get rid of the 4 pi out the front and exponential both sides, then I can write this conserved quantity in terms of these new non-dimensional variables in this form. And so this messy looking equation, which I think I'm missing, no, that's right. So these are all multiplied together. So there's a multiplication sign here. It's multiplied by this bracket here. This all equals some constant C, where now we introduce D as being the non-dimensional radius of our cylinder. Okay, so we're interested in trying to identify a critical value for C such that there's a curve then in the R alpha phase plane where when C equals this C critical, there's a separatrix between the periodic leapfrogging motion and non-leapfrogging motion. So here's some examples of what that phase plane looks like. So the key thing here is the black contour in this case. So this is a case when this quantity mu, which is the ratio of the vortex strengths, is positive. So when that ratio is positive, you get a phase plane that looks a bit like this. So we have a region of periodic flow inside this separatrix contour, and then outside here we get non-periodic flow. So this is non-leapfrogging motion, and in here is leapfrogging motion. So if we can calculate the value of C critical, we can determine this separatrix contour, or this contour which has the separatrix on it, and hence we should be able to identify whether we're inside that contour or outside that contour, hence whether we have leapfrogging or no leapfrogging. So the cases where mu is positive and mu is negative are somewhat different. So when mu is positive, this separatrix occurs at a over pi, or a is equal to plus or minus pi effectively. So a over pi is plus or minus 1. But when mu is negative, then your phase plane looks slightly different. You still get the periodic motion. There's a black contour here. You can't really see it, sort of hidden behind these red contours. Non-periodic motion out here. But now the separatrix lies very, very close to the bottom of this figure. So there's a range of R values over which you can you actually get solutions, and it falls sort of right at the bottom here. There's a separatrix down here, and inside that contour you get periodic motion, and outside you don't. But as I say, those two cases are just slightly different. Okay, so how do we find this separatrix, this saddle point? So what we do is we consider this function f, so f plus or minus, so f plus is the case when mu is positive, f minus is the case when mu is negative. So when f is positive, essentially what we do is we go back to our function here. We know the separatrix from sort of numerical calculations falls when a is equal to pi. So we put a equal to pi in this expression, and that gives us f plus, and f minus we know occurs when cos a is equal to 0, and so we put 0 in here and we get f minus. Have I got them the right way around? I think so. Yeah, so okay, so yes, when a is equal to pi, this becomes a plus sign, and that's the f plus. And when a is 0, this becomes a minus, and that's the f minus. Okay, so essentially what we now do is we plot this function f in both cases, and whenever we get a real value of f, then we know that that's a non-periodic leapfrogging result, and then as we get a non-real value of c of it, then we know that that's a periodic leapfrogging motion. Why? Essentially what we're doing is we're going along this contour here or this contour here. So down here we get real values of c, and then we reach a maximum value of c here, and then we go back down and we get real values of c here, and the same thing here, but it's the opposite way around. So here we get a minimum value of c, and then we get maximum value here, and then obviously something else happens here, but we're not interested in this sort of part of the region. We're interested in trying to determine the position of this saddle point here. So this is the case when mu is positive. Okay, yeah, so I should also add that we can restrict the values of, or the range of R over which we're looking for. We're plotting this function because what we want is we want both of our vortices to lie outside of our cylinder. So we have a restriction that we want R1 to be positive, R1 to be greater than A, and we want R2 to also be greater than A. So when mu is positive, it gives this restriction on the values of R. So given our radius of our cylinder D and our ratio of our vortex strengths, just G1 and G2, then we look for values of R between those values. So here you can see that that means that F is actually equal to 0, those two endpoints. So these are just 3 different values for 3 different values of gamma 1 and gamma 2. But you can see you get this sort of growth in F, and you reach the maximum in these mu positive cases, and then it decays away. And here's the case when mu is negative. And when mu is negative, in fact, both conditions just reduce to one condition. So we basically need R greater than this value now. That's why there's a minimum value here in R. You need to have R greater than that value, so it's valid all the way up here. Whereas here you're only valid for r between two particular values. And in this case, you find a minimum in this function f minus. So you can see this function comes down, reaches a minimum, and then it very quickly grows on the other side of it before it stops and it reaches this criteria. Now, in the planar case, they had a really nice function. In fact, you could write down this function in a sort of analytical way, and you could find the maximum by using obviously elementary calculus. You differentiate it, you look for the maximum point, and they were able to write that down in terms of a nice analytical function. We don't really have that luxury here. We have to find these minimum maximum values numerically. Okay, but once we find this critical value of C, this maximum or this minimum, then we can sort of ask questions. Like we can say, okay, so if I give you some initial displacement of these vortices in the radial direction, some r0, where that will yeah, okay, so if I give you some initial displacement r0, what's the maximum distance I can separate these vortices in the a direction, in the theta direction, and still get leapfrogging? So here's a calculation which sort of does that. So what you've got here, again, this is a case mu positive and mu negative. So this says that given some cylinder radius, say 0.2, you can have, given this displacement, initial displacement in the radial direction, from somewhere around sort of minus 1.7 up to just above 2, then this tells you the maximum value of A, and you can have up to almost pi, and then down here you have to be much closer together. When they're much further separated in the radial direction, you have to be much closer in the theta direction. But actually, when you have a large radial separation negative, so it just means you switch the vortices round. So but you can have separations almost up to pi and still get vortex leapfrogging. For mu negative, it's much harder to get to that sort of pi separation. It's a much smaller band of particular values of radial separation and size of the cylinder, but you get sort of quite considerable regions of the parameter space where you see this leapfrogging. So what does it look like? Okay, so here's a particular case, mu 0.8, cylinder radius by 0.6. So this is plotting similar to what we saw before. Instead of x against y, though, we plot the radius against the theta value. And you have two vortices. In fact, they're going the opposite direction this time to the plots we saw before. So you have two vortices, one starting around r is 1, theta is 0, and one starting around r is about 1.3 here, and theta is just positive. And what you see is this leapfrogging, but it's going backwards in this direction here. So it's going counterclockwise around the cylinder. And here's the sort of pattern you get when these vortices leapfrog. And in fact, I should have a video which hopefully demonstrates this. So this is a bit slower than the one we had before, but you can see what's going on here. See, this blue vortex is moving out to a larger radial value. The red vortex is moving inwards. And in a minute, what it does is it will race past the blue vortex. And then the blue vortex starts to move inwards, so it moves in the opposite direction. It's going clockwise, and it'll start to come counterclockwise. Sorry, it moves counterclockwise. It now starts to come clockwise again. And then in a minute, it races through the red vortex, and it continues on in this vein. Okay, and here's a second case. So this is slightly different values of mu, same cylinder radius. and you get the same effect. So what happens is you're just getting larger periods now as you move towards the edge of this leapfrogging region. So this again the XY plane. This is the r theta plane. And then in the planar case, if you moved outside this region, then what you got was you just got one vortex trailing the other one. You didn't get any other particular motion of any type. But in the vortex case, then what can happen is that eventually these vortices will catch each other up. You know, they must see each other again. They don't just one doesn't just pull away from the other one and doesn't see the trailing one. But what you see is when you go outside this region, you actually get the vortices tend to move in opposite directions. So in this case, you got the red vortex is going in the counterclockwise direction as theta increases, and whereas the blue vortex is going in the clockwise direction, theta becoming more negative. And this leapfrogging, though, is much easier to see when you plot the radial values, these alpha 1 and alpha 2, as a function of time. So line results 1 and 2 on this left-hand figure. So this would be mu as positive. Sorry, this is when mu is 0.8, d is 0.6. But what we're doing is we're changing the separation slightly. So down here, these are very close together. You got this fast leapfrogging motion with a small period, whereas here period increases as we move towards the boundary. And then in the third case was the third case we saw where these vortices now move in opposite directions and you don't get any leapfrogging motion. Same is true when you decrease the size of the cylinder. Again, you get leapfrogging motion. Then as you get close to the boundary, it's the same thing is true for the larger vortex case, but you do start to see these vortices will leapfrog, but then switch direction that they're leapfrogging around the cylinder. That's sort of essentially what you've got here in this result 5. And then obviously they then separate and go their opposite direction. For small vortices, for small cylinders, sorry, there is a case where you can see the two vortices moving sort of as a pair. They go the same way around the cylinder, but they're sort of, this is if they're significantly separated. So this is like another region where you don't get leapfrogging, but you get a different type of motion to what we see in 6. Okay, so how are we doing? Okay, let's move on. So one question is, how can we look at other types of geometry given, you know, we looked at the cylinder, we can understand, there's the work of Berkshire who's done the planar wall case. Can we go any further? Well, work of Safman in 96 said, okay, if I take some conformal mapping from two complex planes, little z plane to the capital Z plane, then the Hamiltonian for that is related by this Hamiltonian here, where this okay, so where h of z is the Hamiltonian for two vortices next to a planar wall, g is obviously that conformal mapping, and this w hat function is chosen to ensure that the circulation around whatever closed body you have in your little z plane is 0, i.e. the only circulation in the flow is that due to the two vortices themselves. So this Hamiltonian for two vortices next to a wall, we can write that down. This is in that Berkshire paper, but it's well known, easy to calculate. And so if we define our G, then we can map, in effect, our planar wall case to different geometries. And so hopefully we can say something about leapfrogging in different geometries. For example, if I choose this complex conformal mapping G, and I choose this function W hat, then we get back to the circular cylinder problem that we've just looked at. So the question is, what other geometries could we potentially consider? Okay, but before we consider some other geometries, we just need to think a little bit about the problem. So if you just have two vortices in an unbounded domain with no walls, then you get four conserved quantities of the system. You get the Hamiltonian, like the energy. You have the center of vorticity, the real and imaginary parts of this thing. And you have this angular impulse. This is this rho zero that I had in previous slides. In the planar case, they conserve the Hamiltonian and you conserve the imaginary part of this center of vorticity. In the cylinder case, you have two conserved quantities. Again, you have H and we conserved I. As you go to more general problems, the problem is that you can't conserve two quantities anymore. And so in fact, you're left with only having one conserved quantity. And then it makes doing this sort of analysis a little bit more tricky. So something I did do a little bit of preliminary work on, so just show you a few preliminary results on this. What I want to do is I want to consider two vortices next to a wall with a gap in it. Okay, so I want to consider this sort of geometry here. So thanks to work by Ted Johnson and Rob McDonald, they considered the case of a single gap next to a wall, and that gap has length 2L, and it's given this complex. So this conformal mapping maps the upper half plane where we can put our two vortices next to a solid wall down here to this upper and lower half plane with a solid wall along here, but with a gap in it. And this dotted line here maps to the dotted line in the little z plane. But as I said, the problem with this is doing any analysis on this problem is really difficult because actually you only have one conserved quantity. So you like to have two conserved quantities because then it means that you can effectively use that to eliminate some of your variables. Hence, at the moment, I haven't done any analysis on this and I just have some numerical, preliminary numerical results to show on this. Okay, so here's some preliminary results. So what you're seeing here is a solid wall with a little gap in it at the origin, and then the solid wall going off in this direction. So this is the X direction, this is the Y direction. And this little square that you see here around -40 and about, I think, 1 or 2 is a vortex. So the question is, if I put another second vortex anywhere in this plane, what type of motion do I get? Well, these dashed lines are the expected leapfrogging motion criteria for a completely solid wall, starting with a vortex at this point. But obviously, if as these vortices move, they may well see this gap in this wall, and so you might get a change in types of motion you get. Well, what you see is in fact 3 different types of motion here. So you see those that start somewhere in the yellow region, and those vortices that start somewhere in the yellow region give vortex leapfrogging that we saw for the solid complete wall case. So that's shown in this image here. So if you've got 2 vortices, one starting here, the blue vortex, the red vortex starting a bit further up here, somewhere in this yellow region, then what you see is they just leapfrog. And it just so happens as they get to the gap in the wall, there's a slight change in their period, but nothing that really affects them. And so they just keep leapfrogging up here, and they leave the domain in the sort of upper right quadrant. Then you get the purple region where you get no leapfrogging. And then what you get is this blue region where you get sort of quite interesting results. So in this case, you again get leapfrogging, but instead of leaving the domain in the upper right plane, they leave the domain in the lower left plane. So here's one case below. So this is a case started in this very small blue block. No, it's not. This is one in this blue block down here. Around X is about sort of 20, Y is about sort of -3. So what happens here is the blue vortex starting here just moves along the wall as if it's just seeing the wall. It doesn't see the second vortex, and the same with the red vortex, just moves along this wall, moves in the opposite direction because it's on the underside of the wall. And then the blue vortex is dragged through the wall. So this was known from the works of Johnson and McDonald, who looked at a single vortex in this problem. And then it just so happens that they meet each other at a particular time, because this is just a certain distance away from the gap that they meet just as the second one passes through the wall, and then they leapfrog in this lower half plane. And you get the same thing here. Oh no, sorry. Yeah, okay, sorry. So this is, you get a similar sort of result here with this blue dot, except they leapfrog up here, and then they both go through the gap together and continue leapfrogging. Now, in some of these purple areas here that are within this dashed line, then what you get is you expect them to leapfrog initially, and that's exactly what you see. But then what you find is, for some reason, they stop leapfrogging for large time. So you get leapfrogging for small times, but the large times there's no leapfrogging, because in this case, for example, the blue vortex is dragged through the wall, whereas the red vortex is not. And obviously, this sort of analysis is now sort of dependent upon where you start this initial vortex, because in the case from Berkshire's work, it didn't matter where you start them because the wall was completely solid. So there was this translational invariance. It didn't matter where you start them, but the case that's different now. So if we start our vortices closer to the wall, then this region where you get vortex leapfrogging in the upper half quadrant becomes a bit smaller, but then you get another region down here where you do get leapfrog in this upper half quadrant. So it just so happens that the vortex gets dragged through and they continue off in this direction, and you get another region here where again this vortex will get dragged through and these will continue leapfrogging off to the left. And then if you move just to the right of that gap, because obviously the initial, this has got a positive circulation, so its motion is solely to the right up here, then what you see is you lose this second type of leapfrogging off in the bottom quadrant, but you do get a few regions where you also get leapfrogging, where these are dragged, these vortices are dragged through the gap and then leapfrog off in the upper half quadrant. Okay, so just okay, so for two vortices external to a circular cylinder, we've identified this criteria where the vortices leapfrog within this criteria, and then if they don't satisfy this criteria, there's no leapfrogging. We've highlighted that with conformal mappings, we can consider, in effect, any geometry which can be conformally mapped from the upper half plane. So that this case we highlighted was one of a single gap in a wall. You can also do multiple gaps in a wall is another possible example. And for the case of a horizontal wall with a gap, we identified this leapfrogging in sort of two different contexts and a non-leapfrogging motion. So you have this leapfrogging off at large times in the upper half, in the upper right quadrant or in the lower left quadrant. However, because there's only one invariant of motion in this problem, it makes sort of analytical progress that little bit more problematic. Okay, so thank you very much. Thank you for listening, and hope you enjoyed it, or I hope you got some work done.
Yeah, thank you very much, Matt. It's very interesting subject. Mark, could you ask your question?
Hello, Matt. Thank you very much for a lovely talk. Really interesting results that you found. I put in the chat a question about the circular cylinder case.
Okay.
If you have two vortices set up somewhere, can you arrange it so that the two vortices will ever escape from the circular cylinder, or are they in some sense always bound to it?
No, they're bound to it. I think I've got to remember this now. I think you can only get them moving away if in the case when their circulations are this equal and opposite, and we don't consider that case. I think that's the only case when they then move away from the cylinder as a pair. Otherwise, they don't know that they don't they are bound to it, as you say.
Okay.
Perfect. Thank you.
Yeah, Mark Bly, do you have a question? Mark?
Yeah, thank you, Sasha.
Yeah, yes.
So, thanks, Matt. That was really nice. Yeah, nice calculations. Thank you, and a nice talk. I'm kind of curious about the bit you talked about at the end, where you have the gap in the wall. How did you decide what length that gap should be, and does it matter?
It does matter, and obviously that's another parameter in your problem. So in this case, I think I just set it to be 1 or something. I mean, maybe 2. I think I might set L to be 1, so the gap width is 2. But yes, if you make the gap bigger, then there's more. I think what that does is it opens up more of this lower quadrant to vortices passing back through, and these two things sort of meeting up and being dragged through. But yes, it's just another parameter in your problem. So yes, it does make a difference. The answer is I can't really remember what the difference is, because these are sort of all fairly preliminary. But yes, it does. And sort of nice things you can do with this is sort of add on external flows and stuff as well, and you can sort of see the effect that they have. With a single gap, you can do a flow where there's a flow through the gap from sort of minus infinity to plus infinity, and so you can then drag more of the fluid through, and obviously it just introduces more parameters that you've got to play around with. But yeah, I'm sort of interested at this stage to see what different types of results you could get without then examining so what I'm really quite interested in doing is in the two gap case, you get obviously a separate little island, and then you've got questions like, can you get your vortices to come from different parts of the plane and then end up leapfrogging around this island? And the answer should be yes, because obviously you can just reverse time for these inviscid problems. So if you start off with an initial condition in that case where they then, as Mark says, go their separate ways, then you just reverse time, and so you should be able to find these sort of nice. I think you can then find these little nice little results.
Okay, yeah, thanks, Matt.
Thank you. Paul, please.
Yes, really good, Matt. It's probably a very, very naive question here, but if you just let the radius of the cylinder tend to infinity, does that overlap with the flat's wall base?
Yes, yeah, that was good. Were you my referee? Because that's exactly what they asked. No, that was a very good question that the referee of the paper asked me, and yes, it does. That is exactly true. You can show that in that limit. I can't remember exactly what the limit is now, but yes, effectively, it's the letting r tend to infinity. You get back to the same equations and the same result.
Okay, thanks.
Matt, I also have a question. You mentioned that there could be external flow in addition to the vortices, but if we make it a little bit more complicated, if we say the cylinder is say elastically supported, it's not stationary, so then the vortices together with the cylinder can make a very interesting dance, a very interesting motion, and there could be instabilities like not flutter, but some instabilities of that cylinder depending on the support and other things. And but that is, I believe, it's complicated question, complicated to do, but could be interesting to do this. It's more, it's simpler to do to calculate the forces acting on the cylinder. In your case, it's stationary cylinder, but in the case of leapfrogging, there is the you calculate the forces, and it seems the forces will be periodic, could be, but
I think so, yeah.
yeah, but could be not very smooth. Could be, you know, like beating or
Could
something.
could be, yes, yeah, possibly.
So if to add, because what you did, as I understand, it's kinematics of vortices, right?
Yeah.
If to add a little bit dynamics, it would be, yeah, you know, even more interesting problem. But it's really interesting what you did. Yeah, so this is amazing what's possible to do with the vortices. Yeah.
No, thank you. That's really useful. No, that's something that's worth considering. Thank you.
Yeah. But we have not other questions, so could be. I cannot see other questions. Yeah, so could be the last question for me. At the beginning, you showed the three-dimensional video. It's vortex ring, and they go one through other. And you said it's similar to two-dimensional line vortices. But is it possible at all to do similar things for vortex rings?
That's another really good question, because that's what someone else asked me, whether we could do this. And what was the problem? I think what's really difficult in the vortex ring case is working out, you have to work out a Green's function in the vortex ring case. And in the case when there's nothing in the middle, I mean, that's difficult enough, but you can do that.
Yeah.
And what I started doing was trying to work out what the Green's function was when you put a cylinder in the middle, and it became much more difficult. And it wasn't clear that even if you could do it, whether or not you'd get something sensible. But in theory, yes, is the answer. You absolutely can, if you can deal with this horrible Green's function that you need to calculate for the 3D case.
Thank you very much, Matt. I missed one question from Peter Hicks. Peter, are you here?
Yes.
Hi,
Hi, Matt.
Peter.
Everybody.
Hi, Peter.
How are you doing? Just a couple of quick things myself. When you have this leapfrog around a circle, can you set up the initial vortex position so that the pattern produced is periodic around the circle, or does it actually does the sort of pattern present some sort of procession around the circle as it moves round? And then the second part of the question, could you do something similar with sort of ranking bodies?
I'm not sure about the first one. I assume that you probably can. There's probably one very special point or something where you can get these periodic motions, you know, such that they're I mean, they're obviously yeah, okay, so you want them to repeat, right? So yes, probably is the answer. I didn't look at that, so I can't say, but probably. And can you do the same? Yes, I suspect you can do it with ranking 40. So what McDonald and Ted Johnson did, what McDonald and Ted Johnson did when they were looking at a single vortex in these sorts of geometries, like with the gap and stuff, they would look at the trajectories, but then they would do contour dynamics and look at a vortex patch. So what you could do is you could do sort of general vortex patches. It's a little bit more tricky around the cylinder, but actually the one case where you can do it numerically is when you've got two gaps, because you map to a domain where you've got two solid walls and then periodic conditions either end. And so actually you can solve the Navier-Stokes equations in there. I started to do it because I thought, oh, that might be interesting. And then term started. So yes, you can. It becomes more difficult. I mean, could you do it with ranking? Yeah, you could, but again, it's then more difficult because you're sort of trying to solve the full Navier-Stokes equations.
So you don't think you'd have two conserved quantities in that case?
You should do. I mean, I would think you should do, because you would probably, if you consider the sort of limit as these things Oh, well, you'd have to consider their strength tending to infinity as they become small. But maybe there is a link, isn't there, between point vortices and ranking vortices in this sort of special limit as they shrink down and the vorticity goes to infinity. So possibly.
Yeah.
Thanks, Matt.
So yeah, thank you, Peter. Thank you, Matt. So we should finish our seminar. We already 5 minutes even left.
Sorry.
But no. It was so interesting, Matt. It's a very good presentation indeed. So congratulations from me and from all of us. It's amazing. So I just to remind to all our participants before we end. So there will be seminars also next semester, and it's likely that it will be the same time, Monday at 2. Could be at 3, but likely at 2 p.m. So just the same time. So please send me names you want to invite, or it would be great if you yourself make a talk at our seminar. As to Mark Bly, I understand that he should do so-called inaugural lecture, but it's in 1 year. So if Mark Bly decides to do training for this inaugural lecture, he is very much welcome to do this in our seminar. Inaugural lecture, Mark, is very important part of of professorial duties.
Are you saying you'd like me to give a seminar session?
Yeah. But no, for training, because the inaugural lecture, it will be for the university. Yeah. So last inaugural I attended, it was by Emilian, yours. I believe it was yours. Yeah. So this is the kind of, it's interesting. It's interesting just to know everything what you did.
Are they even doing inaugural lectures at the moment with COVID?
They've done it so far. I don't know what. I mean, I guess not this stuff.
Yeah, it's even simpler by online, Mark. It's even simpler in some sense. Yeah.
I'm happy to give a seminar session if you'd like. That's fine.
Yeah. Very good. So then, in any case, I will send. Yes, no thank you reception online. It's it's pity. It's pity. Yeah, Paul, you're right. So I'll send an email asking for your suggestions for the next semester. And with this very good seminar, very nice presentation, we are closing our semester, series of seminars dedicated or to memorize the retirement of Mark Cooker. I believe it was a very good session. And thank you, Mark, Mark Cooker, in some sense, for giving this chance for us to collect so many nice speakers. So many nice speakers from all around the world, and your friends, your colleagues, and the people working with you, together with you, your students. So it was very good. So I don't know who is retiring next time.
Sasha, I'm very grateful to you for organising this, and to all the speakers, particularly Matt today. There's some fantastic talks. I really enjoyed all of them. Thank you.
Thank you, Mark. Thank you. So then we close this seminar. I'll stop recording, and the talk will be downloaded, and then you can enjoy it again on the YouTube. And also you are free to distribute this link to others who could not attend us today. Okay. So thank you very much, and I'm closing the seminar. Bye-bye.
Thanks, Matt.
Thanks,
Cheers.
everyone. Good to see you all again. Hopefully see you soon.
Yeah, I hope so. Cheers.
Thanks. Bye.